Okay, so this is going to be the solution for exam question 4 from the Physics 116 exam 1 in winter 21, and this is looking at chapter 14. This particular, so the topics in this, the concepts in this question look at chapter 14, specifically section 14.3, College Physics, Knight Jones Field. So we're looking at describing simple harmonic motion, and sort of looking at the kinematic equations. Well, not so much the kinematic equations, but graphing sort of the kinematic quantities for a simple harmonic oscillator, thinking about position time, velocity time, and acceleration time graphs. So in this example, the oscillator is a block on a spring, attached to a magnetic spring on a frictionless surface. The textbook sort of looks at cases in which the block starts at x equals a at time equals 0. In this example, the block is at x equals 0 at time 0 and moving in the negative x direction. But we can think about this from a sort of either a concept based in terms of the forces, or we can certainly think about it in terms of the kinematic equations. So I'll sort of present both ideas. So in this particular case, let's maybe just draw a picture just to start with. Maybe to think just what's happening in a scenario like this. So let's say at t equals to 0, and we know the block is at its equilibrium position. So let's imagine this is the block, and this is x equals 0, x equals plus a, and x equals negative a, and we know at time 0 it's moving to the left at its maximum speed. So since it's moving in this direction, it's going to go towards a negative position after time 0. So this, anytime the object is moving through its equilibrium position, it is moving at its maximum speed. That's where all the potential energy has been converted to kinetic energy. And so as soon as it moves to the left, A is the first position it reaches. So we could sort of think about what would happen in the scenario that it does get to position A. And then sort of extend our ideas from there. So A, let's change that. So the block is somewhere between x equals 0 and its maximum negative position. But let's think about what the forces. You could think about this in multiple ways. So in one sense, it's moving to the left and slowing down, which means the acceleration has to oppose the velocity, which means the velocity is to the right. You could also think about in terms of forces. So we know that the force by the spring is to the right, which is the net force on the block because it's frictionless surface. So if the force is to the right, the acceleration has to be to the right. To the right is the positive direction. So that means that the acceleration at A is positive. It gets even more positive at B. And that's sort of true. So that at the maximum negative position, the acceleration is most positive. So we can sort of add those details in. I'll just write on top of the graph here. Hopefully you can sort of see this. So at B we have positive A max. The acceleration is positive at also position A. As it's coming back, so once it's sort of got to its most negative position, it then returns to the equilibrium position where the acceleration is 0. There's no net force at that point. So the acceleration at C is 0. Then we can see we can do the same logic as the block extends, as the spring moves, the block moves to the right, the spring will start pulling the block back towards its equilibrium position, causing it to accelerate to the left, which is negative. And when the block is at its maximum positive position, this is when it will have its maximum negative A max. So we're told or asked to rank the accelerations from most negative to most positive. B being in the so we're actually going for most negative. So when D being in the most positive position will have the most negative acceleration. C is 0 and both A and B are positive, so it follow it negative going to 0. A is not as a positive acceleration as B, so then it's going to be A, and then at the maximum negative position we have the maximum positive acceleration. So this would be our correct ranking, D, C, A, B. And I know there was a second version of this question, of course, and I guess start with a positive sign, but the same rules apply whenever the object is in a sort of a positive position. The acceleration will be negative. Whenever the object is in a negative position, the acceleration will be positive, and then look at the sort of the maximum and min points. And that's sort of where I want to extend just this discussion slightly. So if we think about the equations of motion sort of for the position, our position curves are generally given if it starts at x equals a at time 0. We have a cosine omega t. And then we know from that equation, if we take the second derivative, a of t is negative a omega squared cosine omega t. But the parts that I want you to sort of consider there is that this is a cosine function and this is a negative cos. So x and a always have opposing trig functions. So in this particular example on the right here, this is a negative sine curve for x. So x of t could be described as negative a sine omega t, which means the acceleration could be described as positive sine. So a omega squared sine omega t. So I think this is a positive, sorry, this is a negative, this position is negative sine, then acceleration has to be positive sine. So we could draw in an acceleration time graph sort of on the same graph, although I can't really treat the axis as, of course, as the same units, because one would be, of course, in meters per second, or sorry, meters for position and meters per second squared for acceleration. But just to sort of show graphically what this would look like, it's sort of maybe somewhat helpful. Let's say I'm going to pick the sort of maximum acceleration to be sort of 3 boxes high, 3 boxes low for the minimum. So drawing my sort of best sine curve for the acceleration. So this is a as a function of time. We can then sort of see that, you know, a matches to a positive acceleration that is not as positive as b, and c of course is 0, and then d tracks to the most negative acceleration. So that's sort of, you know, d being most negative, c being 0, a being positive but not as positive as b. And the same type of analysis, of course, could be applied to the second version. Okay, yeah, I'll wrap up the video there and follow up with question 5.